The vast expanse of space is expected to be orderly, a realm governed by precise physical laws, where celestial bodies follow predictable paths. However, in November of the year 2025, an anomaly disrupted this perceived order. An interstellar interloper known as 3I Atlas, a celestial body barely the size of a mountain, abruptly began to accelerate. This surge in speed occurred without any discernible propulsion, such as exhaust emissions or visible venting, and for reasons entirely unknown. Concurrently, the Sun unleashed a torrent of intense solar flares, causing Earth's magnetic field to experience significant turbulence. Amidst these events, scientist Stefan Burns issued a prescient warning. A substantial energetic wave was approaching. The simultaneous occurrence of these two phenomena, one seemingly celestial and the other terrestrial, raised immediate questions. Was it mere chance, or was there an underlying coordination? Comets, by their nature, are typically erratic. They exhibit sputtering, tumbling, and gradual fading. Yet, 3I Atlas deviated from this pattern, displaying a smooth, deliberate, and remarkably programmed acceleration. This narrative endeavors to trace the silent trajectory of this object through the cosmic darkness, seeking an answer to a single question that could fundamentally redefine our understanding of natural phenomena. If, as authorities suggest, 3I Atlas is simply a comet, then why is it exhibiting behavior characteristic of a sophisticated spacecraft that has just reawakened to its directive? Should this enigma captivate you as it has me, please consider expressing your engagement by clicking the like button and subscribing to ensure you receive every update as this unfolding story progresses in real time. We invite you to share in the comments section your location, the current time in your region, and your perspective on whether we are being fully informed about these world-altering revelations. Furthermore, if you wish to contribute to the expansion of our community, we encourage you to disseminate this video across platforms such as X, Facebook, Reddit, or even within your private group conversations. Your support is invaluable, enabling us to continue investigating such compelling narratives. We express our sincere gratitude for your unwavering backing. Part 1, titled Breakthrough Alert, delves into 3I Atlas's inexplicable propulsion. A disturbance is occurring in the outer reaches of our solar system, a fact that many are hesitant to acknowledge openly. In November of the year 2025, astronomers diligently monitoring the interstellar object 3I Atlas, also catalogued as C-25N1, observed an event that defied established astrophysical principles. The object was not merely following its projected path, but was actively increasing its velocity in a manner inexplicable by gravitational forces alone. The data originating from NASA's Jet Propulsion Laboratory Horizon System, the highly precise computational framework responsible for tracking everything from artificial satellites to asteroids, provided numerical evidence that unsettled physicists. The observed acceleration was resolved into three distinct components, designated A1, A2, and A3, representing directional forces acting upon the object. A1, the radial component, measured approximately 1.662 multiplied by 10 to the -6th astronomical units per day squared, indicating a force directed either towards or away from the Sun. A2, the tangential component, measured roughly 7.089089 multiplied by 10 to the -7th astronomical units per day squared, signifying a force acting along the object's path of travel. A3, the out-of-plane component, registered as precisely 0, a value that was both measurable and, seemingly, impossible. To grasp the significance of these figures, one must comprehend the context of cometary observation. Astronomers frequently detect non-gravitational accelerations in comets. These icy bodies, upon approaching the Sun, heat up, releasing gases and particulate matter into space. This expulsion of material generates a propulsive force akin to a leaking pressurized vessel navigating the vacuum of space. These emitted jets perturb the comet's trajectory from its purely gravitational course. However, the expulsion of gases from a rotating, irregularly shaped icy body is inherently a chaotic process. Jets emerge in multiple directions, the nucleus spins, and the surface is uneven, resulting in propulsive forces acting in all three dimensions: radial, tangential, and, critically, out of plane. 3I Atlas, in stark contrast, exhibited no such disarray. Its thrust was confined exclusively to its orbital plane, suggesting a directed force operating in only two dimensions with a complete disregard for the third. Over a period of approximately 20 days, this sustained acceleration resulted in a change of velocity of about 60 meters per second. This is not an insignificant effect. It represents real, continuous thrust that should manifest tangible evidence. Yet, investigators searching for such evidence found none. No new celestial body had appeared in proximity. No luminous tail trailed the object. High-resolution imaging revealed no discernible jets. For all practical purposes, the object appeared inert. Its apparent magnitude remained consistent, fluctuating between 14.7 and 14.9 with minimal variation. It did not brighten as a comet typically does when nearing the Sun, nor did it display fragmentation or shedding of material in observable quantities. It simply accelerated with silent precision, confined to a single plane. Imagine observing a boat gliding across a lake without any visible means of propulsion. No engine, no sails, no oars. The water behind it shows no disturbance, yet the vessel steadily gains speed, moving in a perfectly straight line as if guided by unseen tracks. Such a scenario would undoubtedly provoke profound questions. The central enigma concerning 3I Atlas is this: if it is merely a comet, why does its behavior so closely resemble that of a spacecraft? The implications of this situation extend far beyond a single anomalous object traversing our solar system. Should natural explanations prove insufficient, and if every conceivable mechanism offered by physics and chemistry is exhausted, we are left with two stark possibilities. Either we are witnessing an unprecedented natural phenomenon that current scientific understanding cannot account for, or we are observing something that has been deliberately engineered. Both scenarios necessitate a fundamental re-evaluation of our understanding of interstellar objects and carry profound implications for our comprehension of solar system dynamics, the very nature of matter that travels between stars, and indeed the unsettling question of whether humanity is alone in the universe. Around the same time that 3I Atlas began its anomalous acceleration, geophysicist Stefan Burns issued a grave warning. He posited that Earth was entering a period of heightened energetic activity. Solar flares were intensifying, geomagnetic storms were assailing the planet's magnetosphere, and seismic events were occurring in unusual clusters. Burns highlighted a confluence of factors: a recurring 28-day cycle of coronal holes on the Sun, the peak of the torrid meteor stream in early November, a supermoon event on November 5th, and impending planetary alignments. His thesis suggested that these were not isolated incidents, but rather components of a larger pattern, an escalating surge of energy manifesting across multiple cosmic systems. The timing of these events creates a compelling coincidence. Here we have an interstellar visitor exhibiting unexplained behavior precisely when our star and planet appear to be entering a phase of elevated activity. While coincidences are indeed commonplace in the vastness of the universe, where events frequently overlap without any causal connection, anomalies can transform coincidences into potential clues, hinting at a broader, currently unseen context. This presentation will meticulously examine the evidence, the anomalies, and the proposed hypotheses, both natural and otherwise. We will scrutinize the data that causes unease among scientists, explore the challenges of reconciling three-eye atlas with existing cometary behavior models, and observe how these models strain under the pressure of contradictory evidence. We will consider alternative explanations that, while sounding like science fiction, may indeed represent scientific reality. We will contextualize this object within the framework of other interstellar visitors, the energetic environment of our solar system, and the cutting-edge discoveries that are reshaping our understanding of small celestial bodies and fundamental physics. Ultimately, we will confront the question that many are reluctant to voice too loudly at present. What if this object is not simply a comet? What if it signifies something of far greater consequence? Time, 0.5 seconds. Part 2 addresses why the condition of A3 equaling 0 is fundamental. Let us first consider how comets are expected to behave erratically, for understanding their typical deviations will illuminate why three-eye atlas is so profoundly different. As a comet draws nearer to the Sun, solar radiation heats its surface, causing the ice to sublimate directly from a solid to a gaseous state, bypassing the liquid phase. This process generates jets of vapor that carry dust particles along with them. These jets are expelled through fissures or vents in the comet's nucleus. The direction of the propulsive force thus depends on the location of these vents and the orientation of the nucleus at any given moment. The nucleus is almost certainly in a state of rotation, tumbling through space along a complex axis. As it spins, different vents are exposed to the Sun sequentially. The resultant propulsive force therefore varies in three-dimensional space, pushing the comet radially, tangentially, and out of the plane of its orbit. The majority of comets exhibit significant out-of-plane acceleration. The A3 component is seldom zero because the forces of nature are inherently chaotic. Surface features are diverse, rotational states are complex, and the timing of vent activation is influenced by thermal conductivity, subsurface structure, and the distribution of volatile substances. All these factors differ from one part of the surface to another. Consequently, thrust is exerted upwards, downwards, sideways, and in various combinations that fluctuate as the comet rotates and as solar heating intensity changes with distance. Orbital modelers who track these celestial bodies routinely incorporate all three components of acceleration into their calculations because the observational data mandates it. Statistical analyses of cometary non-gravitational forces clearly demonstrate this trend. When examining dozens or hundreds of comets, the distribution of A3 values spans a wide spectrum. Some comets exhibit minimal out-of-plane acceleration, while others display considerable amounts. However, a perfect zero is exceedingly rare. It is possible to observe an A3 value close to zero if the period of observation is brief or if the acceleration is weak. But when sustained acceleration occurs over weeks with a substantial observational baseline, an A3 value of zero becomes a significant statement, indicating that the thrust is confined, controlled, and aligned within a single plane. Three-eye atlas returned an A3 value of zero within the measurement uncertainties of the Jet Propulsion Laboratory's Horizon orbital fitting. The residuals, representing the minute discrepancies between the object's predicted and actual observed positions, do not necessitate any out-of-plane component. The orbital model functions effectively without it. This outcome is not attributable to insufficient data. The observational coverage spanned multiple sites and an extended period. The astrometric precision was exceptionally high. Had there been any significant out-of-plane thrust, the fitting process would have detected it. Therefore, what is the implication when an object accelerates for 20 days without deviating from its orbital plane? It suggests that the mechanism generating this thrust is either remarkably stable or exceptionally precise. For natural venting to achieve this, a scenario would be required where jets are emitted exclusively in directions lying within the orbital plane, never perpendicular to it. This would necessitate a nucleus with a precise geometric configuration, oriented in such a manner, and with vents positioned so that their combined thrust effectively cancels out any perpendicular component while reinforcing the radial and tangential forces. While not entirely impossible, this scenario demands a level of geometric precision rarely observed in nature. One plausible hypothesis involves uniform vent distribution. If the nucleus possesses numerous small vents spread evenly across its surface, and if these vents expel material at similar rates, the individual thrust vectors could collectively produce a net force confined to the orbital plane. However, this requires a high degree of symmetry. It necessitates that the rotation axis of the nucleus aligns in a very specific orientation relative to the orbital plane. Furthermore, it requires that the surface composition and thermal properties be sufficiently uniform to prevent any single hemisphere from dominating the outgassing process. Each of these conditions, individually, is somewhat improbable. When considered together, they begin to appear highly contrived. Another hypothesis centers on an unusual volatile composition. Perhaps 3I Atlas is rich in substances such as carbon monoxide or nitrogen. These are volatiles that sublimate at high velocities but carry minimal dust. High-velocity gas jets generate more thrust per unit of mass expelled, which could account for the observed acceleration without producing a visible coma. Nevertheless, this explanation still fails to address the planar confinement of the thrust. Gas jets emanating from a rotating body should invariably possess out-of-plane components unless the spin axis and vent geometry conspire in a highly specific manner. A third possibility is micro-outgassing. This theory proposes the ejection of minuscule particles at high speeds, but in quantities too small to be detected by current telescopic capabilities. This could explain the absence of a visible coma, but it does not resolve the A3 problem. Microjets, by their very nature, should still vary in direction as the nucleus rotates, thereby generating some out-of-plane thrust, unless the system exhibits an extraordinary degree of symmetry. The condition of A3 equaling 0 opens the door to more unconventional interpretations. If one were designing a propulsion system for a spacecraft, the primary objective would be to align the thrust vector with the intended trajectory. Propellant would not be wasted by thrusting perpendicular to the direction of motion. Engines would be fired within the orbital plane to efficiently adjust speed and direction. A thrust profile that is perfectly planar is precisely what one would anticipate from a controlled propulsion system. This does not definitively indicate that 3I Atlas is a spacecraft, but rather that the observed thrust signature is more consistent with deliberate control than with spontaneous, chaotic outgassing. It is a piece of evidence that fits more snugly into one conceptual framework than another, even if that framework makes us uncomfortable. Consider the alternative. If 3I Atlas is venting naturally, then we are witnessing a celestial coincidence of geometry, composition, rotational state, and timing so extraordinarily precise that it remarkably mimics artificial behavior. While nature can be astonishingly creative, it rarely operates with such meticulous tidiness. If there is no observable venting or coma, then what is generating the propulsive force? Part 3. Absence of coma, tail. Observational paradox examines the observations. Telescopes worldwide have been intensely focused on 3I Atlas as it embarked on its trajectory through the inner solar system. Ground-based observatories, orbital assets, and both professional and amateur astronomers have directed their instruments toward this interstellar visitor. They have meticulously measured its brightness, tracked its position with precision, and diligently searched for any indication of activity. What they have consistently observed is an object of remarkable quiescence. The apparent magnitude of 3I Atlas has remained stable, fluctuating between approximately 14.7 and 14.9. For context, this brightness is far too faint to be visible to the naked eye, but well within the range detectable by moderately powerful telescopes. Crucially, its brightness has not exhibited the typical variations one would expect from a comet that is becoming active as it approaches perihelion. There have been no sudden flares in brightness, no outbursts, and no gradual increase in luminosity as sublimation rates climb. The light curve presented a profile more akin to that of an asteroid than an active comet. When a comet undergoes significant outgassing, the consequences are typically apparent. A coma develops, forming a hazy envelope of gas and dust that surrounds the nucleus. This coma can extend for thousands or even hundreds of thousands of kilometers, glowing as sunlight scatters off the dust particles and as molecules fluoresce under ultraviolet radiation. Depending on the viewing angle, a tail may form, swept back by the solar wind and radiation pressure. Jets, which are narrow streams of material erupting from specific vents on the nucleus, may also become visible. The object's appearance undergoes a transformation, its brightness fluctuates, and its morphology becomes intricate. 3I Atlas has displayed none of these characteristics. High-resolution imaging has failed to resolve any substantial coma. No prominent tail has been observed extending behind the object. Publicly released data shows no visible jets. The object has consistently appeared point-like, resembling a barren rock rather than an outgassing comet. Spectroscopic observations, where available, should have revealed emission lines from volatile gases such as water vapor, carbon monoxide, carbon dioxide, or cyanogen. These spectral lines serve as unique identifiers, indicating the composition of substances sublimating from the surface. However, available reports suggest minimal or absent gas signatures, implying that the object is not, in fact, venting material. Now, let us perform some quantitative analysis. To achieve a velocity change of 60 meters per second over a period of 20 days, 3I Atlas must have been subjected to a propulsive force. If this force is attributed to outgassing, we can estimate the mass that would need to be expelled and at what velocity. The fundamental rocket equation states that the change in velocity is equal to the exhaust velocity multiplied by the natural logarithm of the initial mass divided by the final mass. In the case of a small body with an uncertain mass, this calculation becomes speculative. However, we can make order of magnitude estimations. Let us assume the nucleus has a mass of a few million kilograms, perhaps 10 million kilograms, for the sake of argument. To achieve a change in velocity of 60 meters per second, with gas expulsion at a few hundred meters per second, which is typical for the sublimation of water vapor or carbon monoxide, a significant fraction of the object's mass would need to be lost. Let us estimate this loss at a few percent. This translates to hundreds of thousands of kilograms of material ejected into space. The question then arises, where did this material go? Several 100,000 kilograms of gas and dust should unquestionably create a visible coma. Dust particles are highly effective at scattering sunlight. Even if the rate of dust production were low, the accumulation over 20 days should result in a detectable envelope of material. The absence of such evidence observed by astronomers presents a significant challenge. It is possible that the dust-to-gas ratio is exceptionally low, or that 3I Atlas is expelling pure gas with virtually no dust. Gas alone is difficult to detect unless spectral emission lines are observed. However, even plumes of pure gas should be detectable through sensitive spectroscopy. The preliminary reports do not corroborate the presence of strong gas emissions. Another possibility is that the venting is occurring in such minute quantities, distributed across such a vast surface area, that the gas dissipates instantaneously and never accumulates into a dense coma. This would imply the existence of microjets, individually undetectable, but collectively responsible for generating the observed thrust. While plausible, this scenario requires a highly specific surface structure and venting regime. Most comets do not operate in this manner. They tend to concentrate activity in relatively few vents, producing discrete jets rather than a diffuse haze. An alternative explanation might involve the ejection of extremely small particles, such as nanoparticles or even individual molecules, which do not efficiently scatter light in the visible spectrum. Smaller particles tend to scatter light more effectively in the ultraviolet and infrared wavelengths. If 3I Atlas is expelling material optimized for invisibility and optical wavelengths, it could be accelerating without visually indicating such acceleration. However, this hypothesis introduces a further layer of complexity by invoking a very specific distribution of particle sizes and a particular composition, making the natural explanation increasingly intricate. The paradox intensifies. Acceleration implies a force, and if that force originates from mass ejection, it should produce observable signatures. These signatures are conspicuously absent. This suggests either that the mass ejection is occurring in a manner not yet fully understood, or that the propulsive force is not derived from mass ejection at all. If venting is either absent or invisible, what other mechanisms could be responsible for generating the thrust? Part 3 delves into hypotheses of natural outgassing under scrutiny. Let us, for the sake of thoroughness, give natural explanations their due consideration and rigorously examine each hypothesis. Science progresses by testing ideas against empirical evidence, and it is imperative that we exhaust all mundane possibilities before contemplating extraordinary ones. Hypothesis 1. Uniform vent distribution. Imagine the nucleus of 3I Atlas as a roughly spherical object adorned with numerous small vents. Solar heat penetrates the surface, causing the ice beneath each vent to sublimate and escape. If these vents are evenly dispersed and expel material at similar rates, the propulsive forces from individual jets could combine to produce a net force that coincidentally lies within the orbital plane. The operative word here is coincidentally. This scenario necessitates that the nucleus's rotation axis be oriented in such a way that, when averaged over time, the distribution of active vents yields no net perpendicular component of force. For this to occur, the nucleus must possess a specific rotational state. Its axis of rotation needs to be perpendicular, or nearly perpendicular, to the orbital plane, ensuring that as it spins, vents on all sides expel material symmetrically. The surface composition must be sufficiently uniform to prevent any single hemisphere from dominating the outgassing process. Similarly, thermal conductivity must be consistent, thereby avoiding localized hotspots that could lead to intensified venting. While each of these conditions is individually plausible, their collective occurrence represents a remarkably narrow probability. Most comets do not exhibit such precise symmetry. Their surfaces are often uneven, their shapes irregular, and their spin axes are tilted at arbitrary angles. The probability of encountering an object that fulfills all these specific requirements by chance is exceedingly low. Hypothesis 2. Unusual volatile composition. It is conceivable that 3I Atlas is exceptionally rich in highly volatile ices, such as carbon monoxide, carbon dioxide, or molecular nitrogen. These substances sublimate at lower temperatures and with greater velocity than water ice. High-velocity ejection translates to increased thrust for each kilogram of mass lost. If the dust content is minimal, this would result in acceleration without the formation of a prominent coma, sending only text, no instructions or comments. Carbon monoxide undergoes efficient sublimation even far from the sun, potentially accounting for sustained acceleration across a broad trajectory. The physical principles align. Carbon monoxide has been identified in other comets and is known to generate propulsion. However, this concept still confronts the A3 problem. Unless the distribution of volatile substances and the configuration of vents are perfectly aligned, thrust would be expected in all three dimensions. Furthermore, if carbon monoxide were driving the acceleration, spectral signatures of its emission should be detectable. Observers ought to be able to detect it. Their inability to do so suggests either observational limitations or insufficient quantities of the substance. Hypothesis 3 proposes micro-outgassing and mass shedding. Instead of substantial jets, imagine the surface gradually releasing material through a multitude of tiny apertures or via direct sublimation across the entire sunlit hemisphere. While the gas and dust production rate per unit area might be low, when integrated over the whole surface and over several weeks, it amounts to enough thrust to produce the observed acceleration. Because this expulsion is diffuse, it does not form a dense coma, only a subtle haze that current instruments cannot resolve. This scenario necessitates extremely fine-grained activity. The surface must possess sufficient porosity to permit gas to percolate through and escape universally, not just from distinct vents. The thermal wave generated by solar heating must efficiently penetrate the subsurface, driving sublimation beneath the surface layer. The escaping gas must carry minimal dust, or dust so fine that it remains invisible. This represents a delicate equilibrium. Excessive dust would create a coma, while insufficient gas would fail to generate adequate thrust. Achieving this precise balance and maintaining it for 20 days requires a degree of control rarely observed in nature. All three hypotheses share a common hurdle: observational constraints. The absence of a visible coma and tail is not merely a minor inconvenience for these models, it is a central point of contention. Every mechanism proposed to explain the thrust predicts observable consequences, and these consequences are conspicuously absent. We can introduce additional assumptions, invoke special circumstances, and finely tune parameters, but at some juncture we must question whether we are forcing an explanation to fit the data or genuinely following the data's trajectory. Thermal modeling exacerbates the issue. A small celestial body within the inner solar system experiences intense solar heating on its sunward side. This energy fuels sublimation. The rate of mass loss is contingent upon volatile content, thermal conductivity, rotational period, and surface albedo. For 3I Atlas to sustain consistent thrust over 20 days without visible outgassing, all these factors must align in a highly specific manner. The nucleus must be sufficiently small to avoid significant gravitational influence that would hinder mass ejection, yet massive enough to retain adequate volatiles for sustained thrust. It must rotate rapidly enough to distribute heating evenly, but not so rapidly that centrifugal forces become dominant. Its surface properties must be such that dust entrainment is suppressed while gas escape is facilitated. Each additional stipulation narrows the range of possible parameters. What began as a broad category of natural explanations, comets venting when heated, has transformed into a complex challenge requiring extreme precision. None of these hypotheses are inherently impossible. Nature frequently surprises us, but these hypotheses are under considerable strain, and that strain is significant. Therefore, if natural explanations prove inadequate, let us turn our attention to more unconventional possibilities. Part 5 addresses artificial or exotic hypotheses, light sails, propulsion, or unknown physics. We are now entering speculative territory, and it is crucial to acknowledge this from the outset. The following are ideas, not established facts. They are scenarios that align with some of the data but lack definitive evidence. Science demands extraordinary proof for extraordinary claims, and we have not yet reached that point. However, given the anomaly we are investigating, these ideas cannot be dismissed without careful consideration. Hypothesis 1. A thin, reflective sail propelled by radiation pressure. Envision a structure with exceptionally low mass and a vast surface area, essentially a mirror tumbling through space. Sunlight striking its surface is reflected, transferring momentum. The force exerted is small but applied consistently over days or weeks, accumulating over time. The key factor is aerial mass density, or mass per unit area. For a sail to experience noticeable acceleration under solar radiation pressure, it must be exceedingly thin, perhaps only a few microseconds thick, and highly reflective. Let us examine the calculations. Solar radiation pressure at 1 astronomical unit from the Sun is approximately 4.5 micronewtons per square meter. If 3I Atlas possessed an effective area of several square kilometers and a total mass of a few thousand kilograms, its acceleration could reach the observed 10 to the power of -6 astronomical units per day squared. The precise values would depend on reflectivity, orientation, and distance from the Sun, but the magnitude is plausible. A sail would naturally generate thrust aligned with the sunline, primarily in a radial direction. However, if the sail is angled relative to the Sun, the thrust vector would rotate. Depending on its orientation and spin, components of thrust both radial and tangential could be generated, consistent with the A1 and A2 values. The condition A3 equals 0 would be met if the sail's rotational axis or orientation remained within the orbital plane, a scenario not implausible for a thin structure subjected to torques from radiation pressure and potentially interstellar magnetic fields. The absence of a coma is perfectly explained. A sail does not outgas, it reflects light. It would appear as a faint, steady point of light, precisely as observers have reported. The challenge lies in explaining the origin of such a structure. Natural processes do not construct sails. Ice fragments or thin dust sheets might briefly mimic sails, but maintaining their coherence and orientation for weeks is difficult to justify. If 3I Atlas is indeed a sail, it is likely artificial. Hypothesis 2. Controlled propulsion. Assume 3I Atlas is equipped with a propulsion system, whether chemical, electric, nuclear, or of some more advanced nature. This system would operate periodically or continuously to alter the object's trajectory. The thrust would be intentionally directed, accounting for the precise planar confinement observed. The lack of visible exhaust could indicate that the propellant is of a type not easily detected, or that its exhaust velocity is so high that the plume dissipates instantaneously. For a chemical rocket, propellant mass and an engine would be required. To achieve a delta V of 60 meters per second, with a typical exhaust velocity of a few kilometers per second, only a small fraction of the total mass would be consumed. A small spacecraft could carry sufficient fuel. Electric propulsion systems, such as ion drives, operate at much higher exhaust velocities, necessitating even less propellant. The trade-off is power. An energy source, such as solar panels or a nuclear battery, would be needed to operate the engine. This naturally leads to the question, why? If 3I Atlas is a spacecraft, what is its mission? Why would it engage its propulsion system in the middle of the solar system? It might be executing a course correction, aiming for a specific destination. It could be decelerating after an interstellar journey. The thrust might be part of a data collection or communication protocol that we do not yet understand. Or perhaps it is malfunctioning, firing its thrusters inadvertently. Without understanding the intent, we are left to speculate. However, the pattern of thrust appears deliberate, not random. Hypothesis 3. Unknown physics. What if the acceleration is produced by a mechanism not yet characterized by science? This could include dark matter drag, where 3I Atlas passes through a concentration of dark matter particles exerting a subtle force, or electromagnetic interactions, where the object carries an electrical charge and interacts with the solar wind's magnetic field in an unexpected manner, or boundary effects of the solar system, where some characteristic of the heliosphere or the galactic cosmic ray wind influences motion in ways we have not modeled. These concepts reside at the frontier of scientific understanding. Dark matter remains poorly understood. We infer its existence from its gravitational effects on galaxies, but its properties and interactions are still mysterious. If dark matter can exert drag on ordinary matter under specific conditions, then objects traversing regions of higher dark matter density might experience forces. The magnitude required to explain the acceleration of 3I Atlas far exceeds current dark matter models, but these models are, by their nature, incomplete. Electromagnetic scenarios necessitate that 3I Atlas possesses a significant electrical charge or magnetic moment. Interstellar space is permeated by charged particles, including protons, electrons, and heavier ions. If an object is electrically charged, these particles exert forces upon it. The solar wind also carries a magnetic field. Interactions between moving charges and magnetic fields generate forces. Could this explain the observed thrust? The challenge lies in the scale of these forces. The solar wind pressure and magnetic forces acting on a small body are typically far weaker than the observed acceleration. This would require extraordinary conditions or unknown amplification mechanisms. Comparing these exotic hypotheses against the available data, the light sail scenario appears to be the best fit. It accounts for the planar thrust, the absence of a coma, and the consistent brightness. Controlled propulsion aligns almost as well, but introduces unanswered questions regarding motive and origin. Unknown physics represents the wild card, conceptually possible, but lacking a fully developed mechanism. Each hypothesis requires further validation. For a light sail, we would seek measurements of albedo and reflectivity, looking for unusually high values. For propulsion, we would search for directional changes or velocity adjustments consistent with deliberate maneuvers. For unknown physics, theoretical breakthroughs and independent observations of similar phenomena elsewhere would be necessary. The extraordinary nature of these claims cannot be overstated. To suggest that 3I Atlas might be a sail or a spacecraft is not a casual assertion. It is a hypothesis born from anomalies that resist conventional explanations. We are not claiming definitive proof, but rather stating that the data raises significant concerns. When data is unsettling, it necessitates the exploration of all possibilities, even those that sound like science fiction. Now that we have examined the anomaly and the proposed hypotheses, let us broaden our perspective. How does this phenomenon fit within the larger context of interstellar objects, the energy dynamics of our solar system, and less obvious influences? Part 6 delves into interstellar objects and their comparative behavior. Interstellar objects are transient visitors from beyond our solar system. They originated around other stars, were ejected from their home systems through gravitational interactions, and traversed the galaxy for millions or billions of years before encountering ours. Until recently, they were purely theoretical. Their existence was a matter of probability. However, we had never directly observed one. Then, in October of 2017, the Pan-STARRS telescope in Hawaii detected an object moving at an exceptionally high velocity, too great to be gravitationally bound to our Sun. Astronomers rapidly mobilized to observe it before it disappeared. They named it Oumuamua, a Hawaiian term meaning scout or first distant messenger. Oumuamua was peculiar. Its trajectory was hyperbolic, confirming its interstellar origin. Its shape appeared highly elongated, possibly 10 times longer than it was wide, resembling a cigar or a flattened disk tumbling end over end. Its light curve exhibited periodic variations in brightness, consistent with such an elongation. Furthermore, as it moved away from the Sun, it displayed non-gravitational acceleration, a slight but significant propulsion that could not be attributed to gravity alone. Some proposed outgassing as the cause, despite the absence of a visible coma or tail. Others suggested more speculative explanations, including the possibility that it was a light sail, either naturally formed or artificial. The debate surrounding Oumuamua became intense. The majority of scientists favored natural explanations, arguing that unusual outgassing or an asymmetric shape could generate the observed acceleration without a visible coma. A minority, including Harvard astronomer Avi Loeb, contended that the data was more consistent with a thin, reflective object propelled by radiation pressure, potentially an artifact. This controversy underscored our limited understanding of interstellar objects and how quickly initial assumptions can be challenged when data deviates from expectations. In August of 2019, a second interstellar visitor arrived. This object was named 2I Borisov. Unlike Oumuamua, Borisov presented as a typical comet. It developed a prominent coma and tail as it approached the Sun. Spectroscopic analysis revealed familiar volatile compounds, including water, carbon monoxide, and cyanogen. Its behavior aligned perfectly with astronomers' expectations for comets, albeit one originating from outside our solar system. Borisov provided reassurance to the scientific community, suggesting that most interstellar objects are likely ordinary, and that Oumuamua might have been an anomaly rather than the norm. Now we have 3I Atlas, which is neither like Oumuamua nor Borisov. It shares characteristics with both, but fits neatly into neither category. Like Oumuamua, it exhibits non-gravitational acceleration without visible outgassing, prompting questions about the source of its propulsion. Like Borisov, it follows a trajectory consistent with a cometary path, entering the inner solar system and experiencing solar heating. However, its thrust profile, specifically its confined planar motion, sets it apart. Oumuamua's acceleration included radial and tangential components, but also uncertainties that could have masked out-of-plane effects. Borisov's outgassing was clearly three-dimensional, typical of an active comet. 3I Atlas occupies an intermediate position, anomalous, but in a distinct manner. This raises the question, is 3I Atlas simply another interstellar visitor exhibiting unusual behavior, or is it an object of a fundamentally different nature? If we are observing three distinct interstellar objects within less than a decade, each with unique characteristics, What does this imply about their overall population? Extrapolating from such a small sample is perilous. We lack information about selection biases. Brighter objects are easier to detect. Highly reflective or unusually active objects might be overrepresented. We are essentially casting a small net into a vast ocean of possibilities. Consider detection bias. Current surveys identify interstellar objects when they are relatively close and luminous. Fainter, smaller, or less active objects likely escape detection. If a population of low-mass, sail-like structures drifts between stars, we might only detect them when they approach perihelion and become illuminated by sunlight. The same applies to small, inert bodies that appear only as faint points of light. The population of interstellar objects could be vastly more diverse than our 3 observed data points suggest. Imagine a scenario where 3i Atlas is part of a fleet, a swarm of sails or probes deployed by some advanced civilization eons ago to explore the galaxy. Most would pass through solar systems unnoticed, but occasionally one might be detected because it brightens as it nears a star. This is highly speculative, bordering on fantastic, but it is not contradicted by the available data. If intelligent civilizations exist and have mastered interstellar travel or communication, deploying lightweight probes is a plausible strategy. Thin sails, propelled by starlight and carrying minimal payloads, could traverse immense distances over millennia. Alternatively, 3i Atlas might be a fragment, a piece of an engineered structure that fractured ages ago. Perhaps it is a discarded component, space debris from an alien civilization drifting on galactic currents. Or it could be entirely natural, a type of object we have not yet characterized because we have never had the opportunity to study interstellar material up close. It is possible that comets from other stellar systems form in environments different from our own, with compositions or structures that result in unusual venting behaviors. Comparing the behavior across different interstellar objects helps frame whether 3i Atlas represents an outlier or a significant shift. If every interstellar object we discover exhibits anomalies, then anomalies become the norm, and we must adjust our expectations. If 3i Atlas stands alone, it becomes a puzzle demanding a specific explanation. Currently, with only 3 examples, we cannot definitively conclude, but the emerging pattern is suggestive. Interstellar objects do not behave like indigenous solar system bodies. They consistently surprise us, challenge our assumptions, and each new discovery expands the boundaries of what we consider possible. Having considered external objects, let us now turn inward to our own solar system's energy environment and how it might influence such behavior. Part 7 examines the solar system's energy environment, solar flares, coronal mass ejections, and geomagnetic activity. The Sun is not a quiescent, steady ball of light. It is a turbulent nuclear furnace governed by a powerful magnetic dynamo, and its activity cycles through periods of minutes to decades. Currently, in late 2025, the Sun is entering a phase of increasing activity. Solar Cycle 25, which commenced in late 2019, is approaching its peak phase, the period of maximum activity when sunspots proliferate, solar flares erupt, and coronal mass ejections blast plasma into space. Solar flares are sudden releases of magnetic energy stored in the Sun's atmosphere. They manifest as brilliant flashes in extreme ultraviolet and X-ray wavelengths, releasing energy equivalent to millions of hydrogen bombs. Flares are categorized by their X-ray intensity: A-class, B-class, C-class, M-class, and X-class, with each increment representing a tenfold increase in power. M-class flares are of moderate strength and can cause brief radio blackouts on Earth's sunlit side. X-class flares are the most powerful, capable of triggering radiation storms and disrupting satellite electronics. Coronal mass ejections, or CMEs, are even more dramatic events. These involve massive eruptions of plasma and magnetic fields from the Sun's corona, ejected into interplanetary space at speeds ranging from hundreds to thousands of kilometers per second. When a CME impacts Earth's magnetosphere, it compresses the magnetic field, inducing electric currents in the ionosphere and on the ground. Geomagnetic storms follow, producing auroras at high latitudes, disrupting power grids, degrading GPS signals, and exposing astronauts to increased radiation. In 2025, observers have recorded multiple M-class and X-class flares, along with several significant CMEs. The frequency of these events is rising as the solar cycle progresses toward its maximum, anticipated around 2025 or 2026. High-speed solar wind streams originating from coronal holes have battered Earth's magnetosphere, resulting in recurrent geomagnetic disturbances on an approximate 27-day cycle, corresponding to the Sun's rotation period as viewed from Earth. So, what is the relevance of this to 3I Atlas? Small bodies within the solar system are not immune to the Sun's energetic output. Solar radiation and the solar wind affect them in numerous ways. Radiation pressure exerts a force on their surfaces, a phenomenon already discussed in the context of light sails. Charged particles in the solar wind can sputter atoms from exposed surfaces, eroding material atom by atom. Photoelectron emission, where ultraviolet light ejects electrons from the surface, can electrically charge the object, creating electric fields that interact with the solar wind's magnetic field. For icy bodies, solar heating drives sublimation, the primary mechanism behind cometary activity. However, enhanced solar output during flares or CMEs could temporarily increase heating rates, triggering bursts of outgassing. Alternatively, if the object is electrically charged, interactions with the solar wind plasma might exert forces, augmenting or modifying the thrust generated by radiation pressure or outgassing. These mechanisms are subtle, typically producing effects far smaller than the observed acceleration of 3I Atlas, but in principle, they could contribute. The temporal coincidence is intriguing. The anomalous acceleration of 3I Atlas was detected in November 2025 during a period of heightened solar activity. Stefan Burns pointed to this same time frame, noting a convergence of factors: the 28-day recurrence of coronal holes, peak torrid meteor activity, a supermoon, and what he termed a significant wave of energetic disturbances affecting Earth. Is this connection genuine or coincidental? Let us quantify the forces involved. Solar wind pressure at 1 astronomical unit is approximately 1 to 6 nanopascals, depending on whether one is experiencing slow or fast solar wind. For an object with a cross-sectional area spanning 1 square kilometer, the resultant forces would be on the order of millitons. Contrast this with the force necessary to impart an acceleration of 3I Atlas. If the object possessed a mass equivalent to millions of kilograms, forces ranging from newtons to tens of thousands of times greater than the pressure exerted by solar wind alone would be required. Consequently, solar wind cannot be the principal driving force. Radiation pressure, at approximately 4.5 micropascals at 1 astronomical unit, exerts a stronger influence. However, even this falls short unless the object exhibits extraordinary characteristics, such as the low surface density of a solar sail. An augmentation of solar output during solar flares could temporarily elevate radiation pressure by a few percent, which is insufficient to account for continuous acceleration over a period of 20 days. What about electromagnetic interactions? Should 3I Atlas carry a significant electrical charge, perhaps acquired through photoemission or interaction with interstellar plasma prior to entering the solar system, it could engage with the Sun's magnetic field, which is embedded within the solar wind. A charged particle moving within a magnetic field experiences the Lorentz force acting perpendicularly to both its velocity and the field. Depending on the magnitude of the charge and the field strength, this could generate forces. Yet, again, the resultant forces are minor. The solar wind's magnetic field at 1 astronomical unit measures approximately 5 nanoteslas. To achieve substantial force, one would require immense electrical charges far exceeding what photoemission or typical charging mechanisms can provide. It is possible that unknown couplings or amplification mechanisms are at play, where solar activity precipitates reactions on the object's surface or within its interior that have not yet been modeled. For instance, if 3I Atlas possesses a highly conductive surface, rapidly fluctuating magnetic fields from coronal mass ejections could induce eddy currents, creating magnetic moments that interact with the solar wind. This is highly speculative and would necessitate exotic material properties, but it is conceptually feasible. A more probable connection is indirect. Solar activity influences the entire heliosphere, the encompassing bubble of solar wind and magnetic field that surrounds our solar system. Variations in solar output modify the density, temperature, and magnetic structure of this environment. Small bodies traversing this region might encounter different conditions than they would during periods of solar minimum. If 3I Atlas is venting material, enhanced solar heating or altered ambient pressure could modulate the rate or direction of this venting. If it functions as a solar sail, fluctuations in radiation pressure or magnetic torques could alter its orientation, thereby affecting its thrust. The central challenge is that none of these proposed mechanisms definitively explain the observed phenomena. The acceleration is sustained and planar rather than sporadic or reactive to solar flares. There is no evident correlation between flare events and modifications in 3I Atlas's trajectory. The link remains speculative, a compelling coincidence rather than a proven causal relationship. However, coincidences can accumulate. Stefan Burns issued a warning of a significant energetic event, and 3I Atlas began to exhibit unusual behavior. The Sun is experiencing heightened activity, and an interstellar visitor is behaving in an unexplained manner. These events might be independent, or they might not be. The universe is interconnected in ways we are still discovering. Forces and fields permeate space, linking distant entities through subtle interactions. When multiple systems display anomalies concurrently, it warrants an investigation into whether they share a common origin. If our Sun and heliosphere are indeed playing a role, could Earth itself be part of a larger energetic picture? This leads us into the narratives concerning seismic activity and the big wave. Part 8. Seismic Activity, Earth Effects, and the Big Wave Narrative. Stefan Burns may not be a universally recognized name, but within the circles that monitor geophysical phenomena and space weather, his pronouncements carry considerable weight. In late 2025, Burns issued a stark alert. Earth is entering a phase of intensified energetic activity, a convergence he termed the Big Wave. His argument is predicated on the simultaneous alignment of multiple factors, each with the potential to influence geological and atmospheric systems. Firstly, the 28-day recurrent cycle of coronal holes. Coronal holes are regions within the Sun's atmosphere where the magnetic field opens outward into space, permitting high-speed solar wind to escape. These holes can persist for weeks or months, and as the Sun rotates approximately every 27 days, the same coronal hole can repeatedly face Earth, dispatching pulses of fast solar wind our way. Each pulse compresses the magnetosphere, inducing geomagnetic storms. Burns observed that in late 2025, a particularly active coronal hole was generating intense, recurring disturbances, subjecting Earth's magnetic field to significant impacts every 4 weeks. Secondly, the torrid meteor stream. Earth traverses the torrid stream twice annually, once in late October and early November, and again in late June and early July. This stream comprises debris originating from Comet Enki and potentially fragments of larger celestial bodies that disintegrated millennia ago. In early November 2025, Earth passed through the densest portion of the stream, encountering a greater number of meteors and possibly larger particles than usual. Some researchers have posited that meteor impacts, even minor ones, could trigger atmospheric or seismic disturbances, although empirical evidence for this remains limited. Thirdly, the supermoon on November 5, 2025. A supermoon occurs when a full moon coincides with the moon's closest orbital approach to Earth. The moon's gravitational influence on Earth is marginally stronger during these celestial events, leading to an increase in tidal forces. Tides affect not only the oceans, but also the solid Earth, inducing measurable deformations in its crust. Certain studies suggest that tidal stresses may influence the timing of earthquakes, particularly for fault lines already approaching a state of critical failure. Fourthly, planetary alignments. Burns mentioned forthcoming alignments involving Jupiter, Saturn, and other planets, configurations that purportedly concentrate gravitational influences on both the Sun and Earth. While astrologers have long asserted the significance of such alignments, mainstream scientific consensus remains skeptical. The gravitational forces exerted by distant planets on Earth are negligible when compared to the tidal forces from the Moon and Sun. Any discernible effect would likely be lost within background noise. Burns interconnected these elements, contending that their simultaneous occurrence creates a temporal window of heightened energetic activity, manifesting as increased solar flares, geomagnetic storms, and, crucially, seismic events. He cited recent earthquakes, a magnitude 6+ event in Kamchatka, Russia, another in Afghanistan, and tremors in other locations, as evidence of Earth's crust responding to this confluence of factors. The scientific community's reception to such assertions is, at best, mixed. The hypothesis that solar or geomagnetic activity might precipitate earthquakes has been the subject of decades of research, yielding inconclusive results. Some studies indicate a weak correlation between geomagnetic storms and shallow seismicity, particularly in volcanically active regions where magma movement could be influenced by electrical currents or pressure fluctuations. Conversely, other investigations find no correlation, attributing apparent patterns to statistical anomalies or publication bias. The prevailing scientific consensus posits that while external forces such as tides can exert a minor influence on earthquake timing, they do not act as direct causal agents. Tectonic stress accumulates over years or centuries, and external triggers, at best, might nudge already primed fault lines beyond their breaking point. A principal difficulty with the big wave narrative lies in distinguishing meaningful signals from random noise. Earthquakes occur incessantly. Magnitude 6 events transpire hundreds of times annually across the globe. Solar flares and geomagnetic storms are commonplace during periods of solar maximum. Supermoons occur roughly every year or two. Meteor showers are predictable occurrences. When one searches for patterns within noisy data, such patterns often emerge, even if they are merely coincidental. Humans are inherently pattern-seeking beings, and our cognitive faculties excel at identifying connections that may not possess any objective reality. That being said, prematurely dismissing Burns's claims would be ill-advised. Scientific progress is achieved by scrutinizing anomalies and rigorously testing hypotheses. If a genuine physical mechanism links solar activity to seismicity, its discovery necessitates thorough investigation, not reflexive skepticism. Certain researchers are currently exploring how geomagnetic disturbances might impact rock conductivity, piezoelectric effects within rocks, or fluid pressure within fault zones. These are subtle phenomena, challenging to measure and even more difficult to definitively prove, but their existence is not impossible. Now, how does this connect to Three-Eye Atlas? Burns did not explicitly link his big wave concept to the interstellar object, but the temporal proximity invites speculation. If Earth is experiencing an energetic convergence, could analogous processes be affecting objects traversing the solar system? Might intensified solar wind or heliospheric disturbances influence Three-Eye Atlas's behavior? One perspective is that both phenomena could share a common underlying cause. Perhaps the solar system is passing through a region of interstellar space characterized by a higher density of charged particles or dust, impacting both Earth's magnetosphere and smaller bodies like Three-Eye Atlas. The solar system travels through the galaxy at approximately 250 kilometers per second, and the local interstellar medium is not uniform. We navigate through clouds of gas and dust, regions exhibiting varying densities and temperatures. If we have recently entered a denser region, this could amplify solar wind interactions, increase meteor influx, and potentially exert forces on small bodies. Another avenue of inquiry involves electromagnetic interactions. Earth's magnetosphere and Three-Eye Atlas, if electrically charged, both interact with the heliospheric magnetic field. Changes in the Sun's output alter the structure of this field. It is conceivable that the same magnetic fluctuations that trigger geomagnetic storms on Earth also affect Three-Eye Atlas, inducing torques or forces that modify its trajectory. This remains highly speculative and would require mechanisms not yet understood. A third perspective is purely observational. It is possible that the big wave represents a cognitive framework, a narrative that groups disparate events simply because they occur in close temporal proximity. Three-Eye Atlas's anomaly, Earth's seismic activity, and solar storms might be entirely independent, and the act of connecting them could be an instance of apophenia, the perception of meaningful patterns in random data. Science mandates that we rigorously test this possibility. Burns's assertions are not aligned with mainstream scientific thought, and many of his specific predictions or proposed causal links lack robust evidence. However, the temporal clustering of events is undeniable. Multiple systems are exhibiting activity within the same time frame. Whether this is attributable to coincidence, a shared cause, or interconnected processes remains an open question. The big wave narrative challenges us to adopt a holistic perspective of the solar system as an integrated system rather than a collection of isolated phenomena. Beyond the solar and seismic narratives, hidden data controversies and social dynamics within the research community also warrant examination. Let us delve into these aspects. Part 9. Hidden Angles and Controversies Within the Community. Science is ostensibly objective, guided by data and logic, free from bias and political influence. In reality, the process is more complex. Scientists are human beings with egos, career aspirations, funding pressures, and social dynamics that shape what research is pursued, what findings are published, and what ideas gain acceptance. The narrative surrounding Three-Eye Atlas unfolds not only through observations from telescopes and complex calculations, but also within conference rooms, peer review panels, and online forums where ideas collide and reputations are either forged or shattered. Let us commence with data transparency. The non-gravitational parameters pertaining to 3I Atlas are derived from NASA's Jet Propulsion Laboratory's Horizon system. Horizons is a publicly accessible tool. Anyone can utilize it to obtain orbital elements and predictions. However, the underlying data, the astrometric observations that inform the orbital fit, originate from a multitude of sources: professional observatories, amateur astronomers, and sky surveys. Not all of this data is immediately available to the public. Some observations are proprietary, retained by survey teams until their publication. Others are disseminated through the Minor Planet Center, a clearinghouse for asteroid and comet data, albeit with variable quality and completeness. Independent researchers have taken the available data and performed their own orbital fits, posting their results on forums, preprint servers, and social media. Some of these analyses align with JPL's solution, while others exhibit slight divergences, indicating a sensitivity to the specific observations included and the weighting assigned to residuals. Orbital mechanics is a precise discipline, but it is not entirely immune to interpretation. The selection of data points to be trusted, the methodology for handling outliers, and the choice of model for non-gravitational forces all involve subjective judgments. Different analysts arrive at different conclusions, leading to shifts in the results. This presents a challenge when an individual claims that 3I Atlas exhibits zero out-of-plane acceleration. Are they reporting a robust finding or an artifact of their specific dataset and fitting procedure? Peer review is intended to identify such issues, yet much of the discussion surrounding 3I Atlas is occurring outside of formal channels, primarily on platforms like Twitter, YouTube, Reddit, and personal blogs. Ideas spread rapidly, while the peer review process moves at a slower pace, and by the time official papers are published, the prevailing narrative may already be established. Furthermore, there is the question of anomalies in color and reflectivity. Some observers have reported that 3I Atlas appears bluer than typical comets or asteroids, with a spectral signature suggesting high reflectivity or an unusual surface composition. Blue spectral characteristics can indicate the presence of fresh ice, a lack of dust, or specific mineral compositions. Within the context of the light sail hypothesis, a very high albedo and a blue hue would lend support to the notion of a reflective surface. However, accurately measuring color is a difficult task. It is dependent on the phase angle, which is the angle between the sun, the object, and the observer. As the phase angle changes, the brightness and color of the reflected light also shift. Observers must account for this, and these corrections rely on models that may not be applicable to unusual objects. Instrument calibration is also a critical factor. Different telescopes, detectors, and filters all introduce systematic errors. Factors such as sky background noise, atmospheric absorption, and contamination from nearby stars further add to the variability. When someone asserts that 3I Atlas is anomalously blue, it is pertinent to inquire, compared to what, using which instruments, and after what corrections? If the claim is based on a limited number of data points from a single observer, it is suggestive but not conclusive. If multiple independent teams utilizing different instruments confirm the observation, the claim gains considerable strength. To date, the publicly available evidence is sparse, and the scientific community remains cautious. Speculative hypotheses face significant obstacles within academia. Proposing that 3I Atlas might be an artificial object or a light sail typically invites skepticism and, at times, outright dismissal. The peer review system is inherently conservative, favoring explanations that align with established theoretical frameworks. Papers that introduce novel physics or extraordinary claims require exceptionally strong evidence, and reviewers subject them to heightened scrutiny. While this rigor is appropriate for scientific advancement, it can also impede innovation. If every unconventional idea is rejected before the supporting evidence has been fully amassed, we risk overlooking genuine discoveries. There is also a social dimension to consider. Researchers who advocate for unconventional explanations risk compromising their professional reputations. Mainstream scientists may distance themselves, apprehensive of being associated with fringe ideas. Funding agencies tend to favor predictable projects that promise incremental advancements rather than paradigm-shifting breakthroughs. Career progression, tenure, and the acquisition of grants are contingent upon publishing in respected journals, and these publications often prioritize conventional research. Consequently, there exists a bias toward natural explanations, even when the available data strains to accommodate them. Conversely, contrarian researchers who embrace speculative concepts may find themselves isolated, forming their own communities where unconventional thinking is lauded, but critical scrutiny might wane. Echo chambers can emerge where consensus prevails and dissenting viewpoints are disregarded. This dynamic operates on both sides, with the mainstream dismissing fringe theories and the fringe dismissing mainstream science. Social media exacerbates these trends. A single assertion about Three-Eye Atlas, supported by preliminary data, can achieve widespread dissemination before undergoing rigorous vetting. YouTube channels, blogs, and podcasts frequently seize upon anomalies, constructing narratives that attract audiences but may not accurately reflect scientific consensus. Mainstream scientists often respond, sometimes dismissively, thereby creating a perceived division between official science and independent researchers. The public observes this unfolding situation, uncertain about whom to trust. The extent to which community bias or publication bias might influence our interpretation of Three-Eye Atlas's anomaly is difficult to quantify, but its effects are undeniable. If researchers unconsciously favor natural explanations because they are more readily publishable, they might not pursue exotic hypotheses with the same level of dedication. Conversely, if contrarians place undue emphasis on anomalies because they align with their existing worldview, they might overlook mundane explanations that could actually be valid. Ideally, science engages in self-correction through replication, debate, and the accumulation of evidence. However, this process is inherently slow and imperfect. The paramount principle is intellectual humility. Admitting a lack of knowledge is often more challenging than it appears. Scientists are trained to provide definitive answers, and encountering uncertainty can feel like a failure. However, Three-Eye Atlas presents a genuine puzzle. The data does not fit neatly into established categories. Acknowledging this uncertainty, exploring multiple hypotheses without premature commitment, and awaiting more comprehensive data represents the most intellectually honest approach. Having now examined the context and controversies, we shall proceed to map the spectrum of hypotheses and assess which hold greater promise and which are likely to prove unproductive. Part 10. Hypothesis Matrix. Mapping possibilities and probabilities. Let us establish the framework for our analysis. We are presented with multiple competing hypotheses aimed at explaining the behavior of Three-Eye Atlas. Each hypothesis makes distinct predictions, necessitates specific conditions, and aligns with the available evidence to varying degrees. The objective at this stage is not to definitively declare a winner, but rather to map the landscape of possibilities and identify the observations that would most decisively alter our level of confidence. Hypothesis: natural comet outgassing with uniform vents. Required conditions include a cometary nucleus possessing numerous small, evenly distributed vents, an axis of rotation perpendicular to the orbital plane to ensure symmetrical outgassing, uniform surface composition and thermal properties, and a sufficient quantity of volatile material to sustain thrust over a 20-day period. Current evidence supporting this hypothesis includes the object's hyperbolic trajectory, suggesting an interstellar origin, and the well-established phenomenon of ice sublimation in comets. Evidence against this hypothesis includes the absence of a visible coma or tail, a stable brightness inconsistent with significant outgassing, and zero out-of-plane acceleration, which would demand extraordinary geometric precision. Key unknowns are the nucleus's size, shape, spin state, surface composition, and the distribution of volatiles. Plausibility rating: moderate but strained. This represents the default assumption for comets, but the lack of visible activity and the precise planar thrust are difficult to reconcile with this model. Hypothesis: unusual volatile composition, specifically rich in carbon monoxide or nitrogen. Required conditions include a high abundance of highly volatile substances that sublimate at low temperatures and high velocities, a low dust-to-gas ratio to minimize visible coma, and a vent geometry that somehow confines the thrust to the orbital plane. Supporting evidence includes the possibility that interstellar objects formed in different celestial environments might possess exotic compositions and highly volatile substances capable of generating high thrust per unit mass. Evidence against this hypothesis includes the expectation of spectroscopic detection of carbon monoxide or carbon dioxide emissions, which have not been unequivocally reported, and the persistent challenge of explaining the confinement of thrust to the orbital plane. Key unknowns are detailed spectroscopic results and the precise composition of the nucleus. Plausibility rating: moderate, but faces observational gaps. The existence of highly volatile substances is plausible, but the absence of detected gas emissions is concerning. Hypothesis: radiation pressure acting upon a thin, low-mass, sail-like structure. The necessary conditions include remarkably minimal atmospheric density, perhaps mere grams per square meter, substantial light reflection, approaching complete redirection, positioning angled towards the sun, generating forces along both radial and lateral axes, and structural integrity maintained for extended periods of weeks. Supporting observations include a flawless correlation with the absence of a gaseous envelope or tail, since such objects do not release volatile compounds, a planar force naturally produced by a thin structure constrained by rotational influences, consistent luminosity if the reflective properties remain stable, and forces from solar radiation scaling appropriately at the observed distances from the sun. Arguments against this theory involve the necessity for either artificial construction or exceedingly uncommon natural origins and the lack of direct quantification of very high reflectivity or albedo. Nevertheless, crucial unanswered questions pertain to albedo and reflectivity measurements, analysis of the light curve throughout its celestial path, and imaging of its structural composition. The assessment of its plausibility ranges from low to moderate, yet it presents a compelling fit. Should 3I Atlas exhibit sail-like characteristics, this conjecture would gain considerable strength. The primary obstacle is demonstrating the existence of such properties. The hypothesis proposes controlled motion via an artificially constructed vessel. The required circumstances include an integrated propulsion mechanism with a propellant or energy reservoir. Intentional application of force for trajectory adjustments or slowing down, minimal observable exhaust or exhaust too diffuse to be detected, and deliberate actions implying sapience or pre-programmed behavior. Supporting evidence encompasses precise planar force, consistent with controlled engine firings, continuous acceleration over a duration of 20 days, matching the capabilities of an efficient propulsion system, and the absence of a coma aligning with non-chemical propulsion methods such as electric drives. The extraordinary nature of this assertion demands exceptionally robust proof, an unclear rationale for applying thrust mid-journey, and no other indicators of artificial origin such as radio transmissions or organized geometric forms. The principal unknowns include the detection of any signals or emissions, alterations in trajectory signifying maneuvers, and imaging at a higher resolution. The probability assessment is highly conjectural but cannot be definitively dismissed. This represents the most extraordinary proposition and necessitates the most stringent corroboration. Hypothesis: peculiar physical phenomena, such as drag from dark matter or electromagnetic interactions. The prerequisite conditions involve traversing a region with elevated dark matter concentration, density, or a surplus of charged particles, a novel interaction between the entity and the interstellar or heliospheric medium, and effects generating forces in the magnitude of 10 to the -6th astronomical units per day, squared, sustained for weeks. Supporting observations include theoretical feasibility if novel physics exists, and unexplained acceleration suggesting new explanatory frameworks. Evidence against this theory comprises the absence of a theoretical construct predicting such phenomena at the observed intensities, no independent substantiation of anomalous dark matter or fields within this locality, and forces derived from known unconventional mechanisms being far too feeble. Key undetermined factors are measurements of the immediate spatial environment and theoretical advancements in dark matter physics. The likelihood assessment is extremely low, but conceptually remains open. This is the wild card at the extreme edge of possibility, improbable but not entirely inconceivable. For each hypothesis, there exist definitive observations that would decisively influence the probability assessments. The identification of a coma or jets would strongly support natural gas release. The measurement of very high albedo, approaching 100%, would substantiate the sail hypothesis. The observation of trajectory shifts corresponding to intentional maneuvers would favor the propulsion hypothesis. The detection of unusual emissions or spectral signatures might lend credence to exotic physics or reveal its material composition. High-resolution imaging revealing structured geometry would imply artificiality. The analytical framework illustrates the areas of our uncertainty. We critically require superior data: spectroscopy to ascertain or preclude gas emissions, photometry across multiple wavelengths to constrain albedo and reflectivity, astrometry over a more extended arc to refine non-gravitational parameters, and, if feasible, radar or resolved imaging to visualize the nucleus itself. Each measurement narrows the range of plausible hypotheses. At present, we exist in a state of productive uncertainty. Multiple hypotheses remain tenable, and none can be definitively excluded. This situation is unsettling but intellectually honest. Scientific progress flourishes in this environment where data challenges established assumptions and compels deeper thought. The ensuing 12 months will be pivotal as additional observations accumulate and theorists refine their models. In our concluding segment, we will broaden our perspective by examining related scientific developments from 2025 that could inform our understanding and expand the context. Part 11, Recent Advancements in Artificial Intelligence and Astrophysical Surveys in 2025. Astronomy is being inundated with data, which is a positive predicament. The upcoming generation of sky surveys, particularly the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, promises to capture imagery of the entire visible cosmos every few nights, generating tens of terabytes of information daily. Traditional analytical methodologies, where human operators scrutinize images or implement predefined algorithms, are incapable of keeping pace. Enter artificial intelligence. In 2025, multiple research collectives announced significant breakthroughs in AI-driven detection of anomalies within astronomical surveys. Machine learning algorithms, especially deep neural networks, have been trained on extensive datasets comprising known celestial bodies, stars, galaxies, asteroids, and comets. Once trained, these networks can meticulously examine new observations, flagging any entity that deviates from established patterns. An object exhibiting unexpected motion, displaying unusual variations in brightness, or presenting spectral characteristics inconsistent with known classifications, is marked for subsequent investigation. A notable instance arose from a collaborative effort utilizing LSST precursor data. Their algorithm identified several faint moving objects that had previously been overlooked by conventional detection systems. Some were identified as distant trans-Neptunian objects, icy celestial bodies located beyond Neptune's orbit. Others were near-Earth asteroids on atypical trajectories, and one intriguingly exhibited indicators of non-gravitational acceleration analogous to that observed in 3I Atlas. The AI flagged it due to its trajectory diverging from a purely gravitational path, and subsequent analysis confirmed thrust components that did not align with typical cometary outgassing. These techniques operate by learning to recognize what constitutes normal behavior, subsequently identifying outliers among moving objects. Normalcy pertains to following Keplerian orbits, paths governed by gravitational forces. Deviations signal either measurement inaccuracies or genuine physical effects, such as venting, impacts, or in highly unusual scenarios, propulsion. The algorithms are capable of discerning these deviations in data that is too obscure or subtle for human analysts to perceive. When applied to 3 Atlas, AI tools could facilitate the detection of faint coma or tail features imperceptible to standard processing. Machine learning can enhance images, extracting signal from noise by discerning patterns in light scattering or the appearance of faint structures. If a whisper-thin coma encircles 3 Atlas, an AI trained on images of active comets might perceive it where human observers would not. AI also improves astrometry, the precise measurement of object positions. By analyzing thousands of reference stars and accounted for systematic errors in telescope pointing, atmospheric distortion, and detector artifacts, algorithms can refine positions to sub-pixel accuracy. Superior astrometry translates to tighter constraints on orbits and non-gravitational parameters. The A2 and A3 values for 3I Atlas could be refined with enhanced measurements, potentially revealing whether A3 is genuinely zero or merely very small. Beyond detection and measurement, AI is employed for classification. Given an object's spectrum, light curve, or orbital path, algorithms can predict its classification: asteroid, comet, trans-Neptunian object, interstellar intruder. These classifications rely on patterns learned from thousands of examples. When an object does not fit into any established category, it is designated as anomalous. 3 Atlas would likely trigger such a classifier due to its combination of characteristics from multiple classes. Interstellar origin, akin to Oumuamua, potential venting like comets, yet planar thrust and no coma, unlike either. The implications are profound. As survey sensitivity advances, the number of detected anomalies will increase. We may encounter dozens of objects exhibiting unusual behavior, compelling us to expand our current taxonomy. If several display sail-like properties, the sail hypothesis for 3I Atlas would become less extraordinary. If numerous objects exhibit planar thrust, we would need to ascertain what natural mechanism produces such a pattern. Conversely, if 3 Atlas remains unique, its peculiarity is amplified. There is also the consideration of false positives. AI algorithms can be misled, misinterpreting noise as a genuine signal or exhibiting excessive sensitivity to training data. Anomalies identified by AI necessitate human verification and subsequent spectroscopic and multi-wavelength observational follow-up. The process from detection to confirmation involves multiple stages, each presenting potential for error. However, the sheer volume of data renders AI indispensable. We cannot afford for human operators to review every single image. We require intelligent filters that bring the most pertinent cases to our attention. Speculation. What if AI uncovers dozens of sail-like or anomalously moving objects within archival data? Objects that traversed our view unnoticed years ago, suggesting a population of such entities, thereby altering our interpretation of 3 Atlas. Instead of a solitary, peculiar visitor, it might represent a class, natural or otherwise. The existence of a class implies a formation or deployment mechanism, something that generates these objects in considerable numbers. Alternatively, if AI surveys the sky for years and discovers nothing comparable to 3 Atlas, that outcome is also enlightening. It suggests such objects are rare, either due to their natural scarcity or because they are artifacts from a sparse population of probes. Rarity does not confirm artificiality, but it intensifies the enigma. The challenge moving forward involves managing expectations. An increased volume of data will yield more anomalies, but also more noise and misinterpretations. The synergistic interplay between human intuition and machine pattern recognition will define the subsequent era of astronomical exploration. 3I Atlas is positioned at the nexus of these trends, presenting an enigma that demands both cutting-edge instruments and careful human discernment for its resolution. How might advancements in detection and analysis alter our comprehension of 3 Atlas? Within the next 1 to 2 years, we will likely possess improved orbital solutions, more refined non-gravitational parameters, deeper imaging to search for faint features, and comparative analyses with newly discovered analogous objects. Each element brings us closer to a definitive answer. Part 12, Advancements in Solar Physics, a major coronal mass ejection solar flare event. This year, 2025. On March 19, 2025, the Sun unleashed its potent energy. An X-3.7 class solar flare erupted from active region 3962, a vast agglomeration of sunspots situated near the Sun's equatorial region. The flare reached its peak intensity at 1423 Coordinated Universal Time, inundating Earth's sunlit hemisphere with X-rays and extreme ultraviolet radiation. Radio operators reported widespread communication blackouts on high-frequency bands as the ionosphere absorbed the sudden influx of energy. However, the flare was merely the preliminary event. 30 minutes later, coronagraph imagery from the Solar and Heliospheric Observatory, or SOHO, revealed a colossal coronal mass ejection launching outward from the flare's origin. The CME propelled billions of tons of magnetized plasma, expanding into a cloud hundreds of times larger than Earth. Its initial velocity was recorded at over 2,000 kilometers per second, sufficiently rapid to reach Earth in less than 20 hours. When the CME impacted Earth's magnetosphere on March 20th at 1100 UT, the effect was striking. The solar wind pressure surged, compressing the magnetosphere and initiating a severe G4 geomagnetic storm. Auroras illuminated skies as far south as the Mediterranean Sea and the northern United States. Power grid operators reported induced currents straining transformers. Satellite operators repositioned spacecraft to avoid the most intense radiation, and astronauts aboard the International Space Station retreated to shielded modules. This event was not unique. It was one of several significant flares and CMEs recorded in 2025, but it exemplified the Sun's immense power during its solar maximum phase. These phenomena provide a natural laboratory for investigating how solar output influences the space environment and the objects residing within it. CMEs and flares alter conditions throughout the heliosphere. Particle flux intensifies, bombarding planets, moons, and smaller bodies with protons, electrons, and heavier ions. These particles carry energy, eroding surfaces, dislodging atoms into space, and charging exposed materials. For icy bodies such as comets, increased particle bombardment can modify sublimation rates or generate electric fields on their surfaces. Radiation pressure also fluctuates. While the Sun's luminosity and visible light change by less than 0.1% during flares, ultraviolet and X-ray output can increase by orders of magnitude. Objects with high albedo, particularly in the ultraviolet spectrum, experience amplified radiation pressure during flares, potentially inducing temporary variations in thrust. The solar wind's magnetic field, typically a few nanoteslas at 1 astronomical unit, can surge tenfold during CME passages. Rapidly changing magnetic fields induce electric currents in conductive materials. If 3 Atlas possesses metallic components or conductive ice, these currents could generate magnetic fields that interact with the solar wind, producing forces or torques. Could the March 19th event or similar occurrences have triggered or intensified 3I Atlas's anomalous acceleration? The temporal alignment is not perfectly synchronized. 3I Atlas's non-gravitational acceleration was detected in November, months after the March event, yet solar activity remained elevated throughout 2025, with multiple M and X-class flares and recurring CMEs. If a connection exists, it would likely be through sustained environmental modifications rather than a singular event. One possibility is the accumulation of effects. Repeated CMEs and high-speed streams erode surfaces over time. If 3I Atlas entered the inner solar system during a period of heightened activity, its surface might have undergone alteration, exposing fresh volatiles or modifying its reflective properties. This could influence its response to solar heating or radiation pressure. Another perspective involves plasma interactions. The solar wind is a plasma, a collection of charged particles. Objects moving through plasma can develop bow shocks, regions where the plasma flow is disrupted. If 3I Atlas is electrically charged, its interaction with the plasma could be complex, potentially generating forces. During CME passages, plasma density and velocity spike, intensifying these interactions. However, the forces involved are typically minor, substantially weaker than the observed acceleration. Theoretical investigations in 2025 have explored the impact of extreme solar events on small celestial bodies. One study modeled dust ejection from asteroids during CME impacts, finding that electrostatic forces can levitate dust particles from the surface, creating transient clouds. If 3I Atlas is expelling dust electrostatically rather than through sublimation, it might account for the absence of a visible coma. The dust disperses too rapidly to form a concentrated cloud. However, this mechanism generates intermittent, not sustained, thrust. The most probable conclusion is that advancements in solar physics enhance our understanding of the boundary conditions for small body behavior, but do not fully elucidate 3 Atlas. Solar events modify the environment, but the object's response is contingent upon its intrinsic attributes: composition, structure, electrical charge, reflectivity. Without knowledge of these properties, we cannot definitively assert the relevance of solar activity. Speculative consideration. What if 3I Atlas traversed a transient solar wind enhancement, a dense, slow-moving structure ejected from the Sun, and the interaction produced drag or thrust that persisted for days? Solar wind structures can extend for tens of millions of kilometers, and an object moving through one might experience prolonged forces. This is a tenuous possibility. The forces involved are weak, but when combined with other mechanisms, they might contribute. Solar physics demonstrates that the heliosphere is dynamic, not static. Conditions vary based on location, time, and the level of solar activity. 3I Atlas's journey through this environment is shaped by these variations. Understanding solar influences helps establish the range of possibilities, even if it does not entirely resolve the mystery. Part 13. New Findings in Small Body Physics. Sample Return or Comet Mission Outcomes. 2025. In September 2025, the Japan Aerospace Exploration Agency, JAXA, announced a remarkable new series of findings from the extended analysis of samples retrieved by its Hayabusa 2 mission from asteroid Ryugu. Although the spacecraft had returned its precious payload to Earth in late 2020, detailed laboratory investigation of the microscopic grains has continued for years, and the new results published in Nature Astronomy may have fundamentally altered scientists' perceptions of outgassing, surface evolution, and non-gravitational acceleration in small celestial bodies. At first glance, Ryugu appeared well understood. A dark, carbonaceous near-Earth asteroid, highly porous and loosely aggregated, more of a rubble pile than a solid rock. However, the 2025 findings revealed something more profound. Ryugu's grains are riddled with microscopic fractures, nanovoids, and channels, forming an internal structure akin to a sponge. Embedded within are hydrated minerals and trace organic compounds, indicators of past alteration by water. What surprised scientists, however, was the behavior of these grains under vacuum and heat. When subjected to simulated sunlight under laboratory conditions, the samples released gases consistently, even though they appeared dry. This process is not explosive venting, as in the conventional depiction of comet jets erupting from a nucleus. Instead, it is diffusive outgassing. Trapped volatiles, including water molecules, carbon dioxide, nitrogen, and other trace gases, slowly migrating outward through a complex network of pores. The gas release is gentle, uniform, and sustained, producing a continuous, low-level thrust. Researchers estimated that on a body the size of an asteroid, this process could generate non-gravitational acceleration detectable over days or weeks, yet without forming a visible coma or tail. This is where 3I Atlas becomes relevant. If the interstellar object 3I Atlas possesses a similarly porous and volatile-rich structure, this mechanism could provide a natural explanation for its enigmatic, continuous in-plane acceleration, the phenomenon reported by NASA's JPL Horizons in November 2025. Unlike typical comets that vent through localized jets, producing visible plumes and asymmetric thrust, a diffusively venting body would exert thrust uniformly across its surface, generating a subtle, smooth acceleration, precisely as observed. This could also account for the absence of a detectable coma or tail. The gas may be escaping too uniformly and too faintly to scatter light or transport dust in measurable quantities. If the primary volatiles are weak emitters, such as nitrogen, argon, or carbon monoxide, then even the most sensitive spectroscopic surveys might fail to detect them. In essence, 3-eye Atlas might be venting invisibly. However, this elegant theory still presents challenges. The condition of A3 equaling 0 in the JPL orbital solution, indicating no out-of-plane acceleration, remains a persistent issue. Even with diffuse outgassing, a rotating body should exhibit fluctuations in thrust direction unless its spin axis happens to be aligned with its orbital plane, a rare coincidence. Therefore, while the Hayabusa 2 findings expand the spectrum of possible natural behaviors, they do not definitively resolve the matter. The geometry remains significant, and thus far, the numerical data do not align perfectly. Nevertheless, the implications of Ryugu's gentle outgassing are considerable. It implies that the distinction between asteroids and comets is less defined than previously assumed. A body can appear dormant and rocky, yet still exhibit subliminal activity under solar irradiation. Over time, such subtle effluxes could even alter an asteroid's trajectory, or, in an interstellar context, mimic controlled movement. Elaborating further, the European Space Agency's Comet Interceptor initiative, slated for its cosmic voyage in the latter half of the 2020s, released a compilation of preliminary research papers in 2025. These documents outlined its strategic approaches for investigating untouched long-period comets or objects originating from beyond our solar system. Among these studies, a simulated investigation delved into the phenomenon of microjets, which are characterized as narrow, sporadic eruptions of gas and particulate matter. These emissions are too faint to be discerned from Earth, but possess the potential to generate a measurable propulsive force. Based on these simulations, microjets could induce net accelerations in the range of 1/millionth to 1/10 millionth of an astronomical unit per day squared, mirroring the observed behavior of 3-eye Atlas. Crucially, these jets could operate intermittently, their intensity modulated by solar radiation and surface temperatures. Nevertheless, their collective effect might average out to a nearly constant acceleration if the celestial body's rotation and orbital configuration aligned favorably. From our terrestrial perspective, this would manifest as a uniform acceleration within the orbital plane, precisely the same enigmatic signature that currently perplexes astronomers. The Comet Interceptor research also highlighted that the surface's microtexture, encompassing the pattern of fractures, craters, and granular slopes, can significantly influence how sunlight is absorbed and re-emitted. A rugged, porous surface can amplify localized heating and sublimation, even at considerable distances from the sun. When this insight is combined with our understanding of Ryugu's porous composition, the emerging picture portrays small celestial bodies as dynamic, living surfaces perpetually reshaped by subtle physical processes imperceptible at the resolution of telescopes. Concurrently, corroborating findings from NASA's OSIRIS-REx mission, which successfully retrieved samples from the asteroid Bennu in 2023, reinforced this evolving understanding. Analyses published in 2024 and 2025 indicated that Bennu's regolith is similarly fragile and porous, possessing a mechanical strength lower than anticipated, more akin to compacted powder than solid rock. Such a structure could facilitate the outward diffusion of deeply embedded volatiles more readily than previously theorized. OSIRIS-REx also documented particle ejection events during its close proximity operations around Bennu, where small fragments spontaneously detached from the surface without any identifiable vent. Collectively, the Hayabusa 2 and OSIRIS-REx missions have provided a novel perspective. Small celestial bodies are not inert cosmic debris, but intricate quasi-active aggregations capable of producing observable accelerations without readily apparent visual cues. For 3I Atlas, this offers a compelling analogy, though not definitive proof, suggesting its behavior might fall within a spectrum of natural processes that we are only beginning to quantify. Naturally, speculation is rife. Could the microstructure of an interstellar object be even more radically different? Having traversed interstellar space for eons, subjected to cosmic ray bombardment and frozen far beyond the heliopause, its surface might have developed unique reactive properties. Upon re-entering the solar system, sudden solar heating could trigger trapped volatiles in unanticipated ways, much like activating a long-dormant power source. Some researchers have posited that interstellar material might even contain novel ices or amorphous carbon matrices not found in typical comets, which could sublimate differently under solar radiation. Others venture even further. Within more speculative discussions, the consistent acceleration and directional stability of 3I Atlas have reignited comparisons to Oumuamua, whose own non-gravitational acceleration in 2017 sparked debates about light sails, artificial probes, and engineered materials. If 3I Atlas exhibits this similar undetectable steady propulsion, but through a different structural mechanism, porous venting rather than reflected pressure, it could imply that multiple natural pathways can simulate propulsion. Or, as some subtly suggest, it might hint at a deeper underlying pattern among interstellar visitors that remains beyond our current comprehension. The overarching conclusion is both humbling and exhilarating. The more precisely we measure, the more anomalies surface. Hayabusa 2 and OSIRIS-REx have demonstrated that microscopic surface characteristics can influence macroscopic motion. The European Space Agency's Comet Interceptor mission aims to capture one of these celestial bodies in action, perhaps even an interstellar visitor, to observe the invisible physics up close. When this occurs, it could reveal whether 3I Atlas's behavior represents the next stage in the natural evolution of small celestial bodies, or something that defies even that classification. In essence, the key to comprehending a mystery weighing 1 billion tons and drifting between the stars might reside within a few milligrams of dust held captive in a laboratory in Japan. Part 14. Frontier Physics, Dark Matter, Modified Gravity, Hypotheses Regarding Spacecraft-like Objects. We have examined natural mechanisms and even entertained the notion of artificial constructs. However, another category of explanation exists at the very edge of our scientific understanding, involving hypotheses that posit forces or interactions we are only beginning to grasp or have yet to confirm. These concepts necessitate stepping beyond the established boundaries of scientific knowledge and inquiring whether the universe harbors phenomena that our current models entirely overlook. Dark matter, modified gravity, exotic particles, and heliospheric boundary effects each represent a frontier where observational evidence is outstripping theoretical explanation, and where the anomalies we detect might serve as indicators of novel physics. Dark matter stands as one of the paramount unresolved enigmas in contemporary cosmology. Its existence is inferred from the fact that galaxies rotate at speeds that visible matter alone cannot account for. Galaxy clusters remain gravitationally bound, despite an apparent lack of sufficient luminous mass. Gravitational lensing reveals the presence of mass where no visible object is detected. The evidence overwhelmingly suggests that approximately 85% of the universe's matter is of a dark nature, interacting primarily through gravity and potentially through forces we have not yet detected. The fundamental question remains: what is it? Theoretical candidates encompass weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and more esoteric possibilities. Despite decades of dedicated searching, direct detection of dark matter particles has not been achieved, leaving us uncertain about their behavior at minute scales or whether they engage with ordinary matter through subtle interactions beyond gravity. Now, we venture into speculative territory. What if dark matter is not uniformly distributed at the scale of our solar system? What if localized concentrations, streams, or clumps exist that objects might traverse? The Milky Way is believed to contain dark matter, halos, and substructures, remnants of smaller galaxies that coalesced with ours in the distant past. Certain models predict the existence of dark matter streams weaving through the galaxy, coherent flows of particles moving in unison. If our solar system were to pass through such a stream, or if 3I Atlas entered the solar system along a trajectory intersecting a dark matter concentration, could this exert a drag force? The physics involved becomes indistinct here because we lack knowledge of how dark matter couples to ordinary matter beyond gravitational interactions. If dark matter particles were to scatter off atoms or nuclei, even infrequently, they could transfer momentum. An object moving through a dark matter cloud would experience drag, a force opposing its motion. However, the cross-section for such interactions, if they occur at all, is constrained by experimental data to be extraordinarily minuscule. Dark matter is termed dark precisely because it does not interact strongly. To generate a force on the order of 1/10,000,000th of an astronomical unit per day, squared on an object with a mass in the millions of kilograms, would necessitate dark matter densities significantly higher than anything predicted or observed in our galactic vicinity. To quantify this, the local dark matter density near the Sun is estimated at approximately 0.3 gigaelectron volts per cubic centimeter, a density roughly 100,000 times lower than that of interstellar gas. If dark matter particles possess masses around 100 gigaelectron volts and scatter off nuclei with cross-sections approaching current experimental limits, the drag force on a kilometer-sized object would be utterly negligible, many orders of magnitude below what is required to explain 3I Atlas. To achieve a meaningful drag force, one would need either substantially higher dark matter densities, significantly larger scattering cross-sections, or some amplification mechanism. None of these are supported by current evidence. However, what if dark matter interacts via a fifth fundamental force, something beyond gravity and the interactions described by the Standard Model? Some theoretical frameworks propose that dark matter couples to ordinary matter through novel bosons or via portals involving Higgs-like fields. If such a force exists and operates over astronomical unit distances, objects traversing dark matter fields could indeed experience accelerations. The challenge lies in the fact that these forces must be exceedingly weak to have evaded detection in laboratory experiments and in solar system dynamics up to this point, yet paradoxically strong enough to influence 3I Atlas. Navigating this requires exceptionally specific and contrived parameters. Another frontier hypothesis involves modified Newtonian dynamics, or MOND, and its relativistic extensions, such as modified gravity theories. MOND was initially proposed to account for galactic rotation curves without invoking dark matter, by postulating that gravity behaves differently at extremely low accelerations. Within the MOND framework, when accelerations fall below a critical threshold of approximately 10 to the power of negative 10 meters per second squared, gravitational attraction becomes stronger than predicted by Newton's inverse square law. This threshold is comparable to the accelerations experienced at the outer edges of galaxies, which is why MOND effectively explains phenomena at those scales. Could Mond or related theories be applicable to 3I Atlas? The object's observed acceleration is approximately 1/10 millionth of an astronomical unit per day squared, which converts to roughly 10 to the power of -8 meters per second squared. This value is higher than the Mundi threshold, but it falls within a regime where modified gravity effects might still be relevant, depending on the specific theoretical formulation. If gravity transitions smoothly rather than abruptly at the threshold, there could be residual corrections that produce anomalous accelerations. The fundamental issue is that MOND and its variations are designed to explain phenomena at galactic scales, not within individual solar systems. Within our solar system, Newtonian gravity, augmented by general relativity, functions with exceptional precision. Spacecraft trajectories, planetary orbits, and even the subtle precession of Mercury's orbit align with predictions to an extraordinary degree of accuracy. Invoking modified gravity to explain the motion of a single small body necessitates that the modification is somehow sensitive to the object's specific properties, its composition, electrical charge, or origin, in a way that does not affect planets or conventional asteroids. This represents a substantial demand and would signify a profound departure from the universality of gravity, a cornerstone of physics. A related concept involves the heliosphere's boundary and interactions at the periphery of the Sun's influence. The heliosphere is the vast bubble of solar wind and magnetic fields encompassing our solar system, extending roughly 100 astronomical units in the direction of the Sun's galactic motion and less in other directions. At the heliopause, the boundary where the outward pressure of the solar wind is balanced by the pressure of the interstellar medium, conditions change abruptly. The densities of charged particles shift, magnetic field orientations flip, and the environment transitions from being predominantly solar-influenced to being dominated by interstellar forces. 3I Atlas, as an interstellar object, presumably traversed this heliopause. Could crossing this boundary have imparted an electrical charge, a magnetic moment, or some other characteristic that now causes it to interact anomalously with the solar wind or the heliospheric magnetic field? In principle, this is plausible. The heliopause is a complex region where particles are accelerated, magnetic fields reconnect, and shock waves form. Objects transiting this zone might undergo alterations, acquiring surface charges or embedding magnetic fields. However, even if 3I Atlas acquired a charge or magnetization at the heliopause, the forces it would experience from the solar wind within the inner solar system depend on the magnitude of that charge or magnetization and on the local solar wind conditions. As previously discussed, typical solar wind forces are far too weak to account for the observed acceleration. This would necessitate extreme charging, perhaps with the object acting as a colossal capacitor, or unusual magnetic properties that strongly couple with the interplanetary magnetic field. There is no observational evidence supporting such extreme properties, and invoking them without independent corroboration appears to be an unwarranted elaboration. Galactic cosmic rays, high-energy particles originating from supernovae and other violent cosmic events across the galaxy, permeate the heliosphere. Their flux fluctuates with solar activity, and the solar wind modulates their density, reducing it closer to the Sun. Could cosmic rays interact with 3I Atlas in a manner that generates thrust? If the object possesses superconducting materials or unusual electromagnetic properties, it might channel or reflect cosmic rays asymmetrically, thereby creating a net force. This is a highly speculative notion, requiring materials and structures that have never been observed in nature. Then there is the concept of an interstellar wind composed of exotic particles. What if a population of as yet undetected particles exists? Not dark matter, but something else entirely. perhaps sterile neutrinos with subtly different characteristics, or hypothetical particles from extensions of the Standard Model that stream through the galaxy. If these particles interact with matter more strongly than dark matter, but are sufficiently rare to have evaded detection, an object passing through a stream of them could experience drag or thrust. The parameters would need to be exquisitely fine-tuned, common enough to affect 3-eye atlas over a period of approximately 20 days, yet rare enough not to be evident in other observational data, and interacting with just enough strength to produce the measured acceleration without yielding other discernible consequences. All of these frontier physics hypotheses share a common characteristic. They necessitate the existence of new, unconfirmed physics to function. They are not extensions of well-tested theories, but rather speculative additions to our comprehension of the universe. This does not render them erroneous. Science progresses by proposing and testing novel ideas. However, it situates them in a distinct category from natural or even artificial explanations. Natural explanations rely on known physics applied in innovative ways. Artificial explanations invoke known engineering principles scaled up or deployed by external agents. Frontier physics explanations, conversely, posit unknown mechanisms, making them more challenging to test and more susceptible to manipulation to fit any observed anomaly. That being said, historical precedent indicates that anomalies occasionally do indeed point toward new physics. The precession of Mercury's orbit was an anomaly that Newtonian gravity could not fully resolve, and it ultimately led to the formulation of general relativity. The rotation curves of galaxies presented anomalies that spurred the development of the dark matter hypothesis. The accelerating expansion of the universe was an anomaly that gave rise to the concept of dark energy. Not every anomaly signifies a breakthrough. Most turn out to be the result of measurement errors or misunderstandings of known effects. However, some are genuine. The critical question then becomes how to distinguish between them. For 3-eye atlas, the pathway to validating a frontier physics hypothesis would demand multiple lines of evidence. Firstly, the anomaly must persist and become more pronounced with improved data, thereby ruling out observational artifacts. Secondly, the proposed mechanism must yield testable predictions that extend beyond merely explaining 3-eye atlas. For instance, if dark matter drag were a real phenomenon, other small bodies situated in comparable regions should exhibit similar effects. If heliospheric interactions were responsible for generating the thrust, we should observe correlations with solar wind conditions or be able to replicate the effect in laboratory simulations. Thirdly, independent experiments or observations must corroborate the underlying physics, whether through the detection of dark matter interactions, the measurement of modified gravity at relevant scales, or the discovery of the hypothesized exotic particles. None of these crucial steps have yet been taken concerning 3-eye atlas. The frontier physics explanations currently remain conceptual frameworks for contemplating possibilities rather than established theories. While valuable as intellectual exercises, pushing us to question assumptions and explore the boundaries of knowledge, they should not be misconstrued as definitive answers. There is also a psychological dimension to frontier physics explanations. They possess an inherent appeal due to their exotic nature and transformative potential. If 3-eye atlas serves as evidence of new physics, it would be an electrifying discovery, one that fundamentally reshapes our understanding. The temptation exists to prematurely embrace such explanations, to favor the revolutionary over the mundane. Science mandates that we resist this temptation, exhausting conventional explanations first and demanding rigorous proof before accepting radical new ideas. Yet, we must also avoid being so conservative that we dismiss genuine signals of new physics. Achieving this balance is a delicate undertaking. In the case of 3I Atlas, the anomalous nature of the data warrants serious investigation, including the exploration of unconventional hypotheses, but it is not yet sufficiently compelling to overturn established physics or to justify constructing new theoretical frameworks around a single object. Perhaps the most accurate position at present is to state that frontier physics hypotheses for 3I Atlas carry a very low probability, but they effectively highlight the limitations of our current knowledge and the potential for the universe to hold surprises. If 3I Atlas's behavior remains inexplicable after exhaustive scrutiny of natural and artificial mechanisms, and if similar anomalies begin to accrue among other objects or systems, then revisiting these frontier ideas will become more justifiable. Until then, they serve as potent reminders that science is an ongoing, incomplete endeavor, that what remains unknown vastly overshadows what we comprehend, and that maintaining intellectual openness is as critical as maintaining a healthy skepticism. The dynamic interplay between established physics and speculative frontier ideas defines the scientific method. We build upon solid foundations, yet remain vigilant for nascent cracks, anomalies that defy easy categorization and which might indicate something more profound. 3I Atlas represents such an anomaly. Whether it ultimately cracks the foundation or proves to be a peculiar but ultimately natural phenomenon remains to be determined. However, the very act of posing these questions, entertaining even the improbable possibilities, and designing observations to test them is precisely how scientific progress is achieved. In our concluding section, we will synthesize these insights to provide a forward-looking perspective and outline key observations to monitor over the next 12 months, along with their broader implications. Part 15. Synthesis and Forward Look. What to watch in the next 12 months. We have embarked on an extensive journey together, commencing with the initial anomaly of 3I Atlas's unexplained propulsion and progressing through natural hypotheses that strain under scrutiny. We have ventured into exotic possibilities of sails and propulsion systems and explored frontier physics at the very edge of our understanding. We have contextualized this object in relation to other interstellar visitors, examined the energetic environment of our solar system, and considered the social dynamics that influence how science interprets anomalies. Now, it is time to step back, take stock of our current knowledge, acknowledge what remains unknown, and look ahead to the observations and discoveries that may resolve this mystery or deepen it further. Let us begin with what we can assert with a reasonable degree of confidence. 3I Atlas is traversing the inner solar system on a hyperbolic trajectory consistent with an interstellar origin. It is exhibiting non-gravitational acceleration characterized by radial and tangential thrust components, designated as A1 and A2, respectively, while demonstrating zero measurable acceleration outside of its orbital plane, meaning A3 equals 0. This acceleration has been sustained for approximately 20 days, resulting in a velocity change of about 60 meters per second. Observationally, the object appears as a faint point of light with a magnitude ranging between 14.7 and 14.9. It shows no significant fluctuations in brightness and no clearly resolved coma, tail, or jets in publicly available imagery. Spectroscopic observations, if they exist, have not reported strong emission lines from typical cometary volatiles such as water vapor or carbon monoxide. Now, let us enumerate what remains unknown, a list that is both longer and more consequential. We do not know the precise size or shape of 3I Atlas's nucleus without resolved imaging. We can only estimate these parameters based on its brightness and an assumed albedo, and this albedo itself is currently unknown. A dark object would appear faint for its actual size, whereas a bright, reflective object would appear faint because it is small. The spectrum of potential sizes for this object spans many orders of magnitude. Its mass remains unknown. Without knowing both its size and density, its mass is entirely unconstrained. However, the mass is absolutely crucial for determining the forces required to achieve the observed acceleration. We lack information about its surface composition, the types of minerals adorning its nucleus, the volatile substances it might contain, or how its reflectivity varies across different wavelengths. Furthermore, its rotational state is a mystery. Its speed of rotation, the orientation of its axis of rotation, and whether it spins steadily or tumbles erratically, are all undetermined. Its thermal properties are also unknown. Specifically, how efficiently it absorbs and radiates heat, and how heat conducts through its internal structure. We are also ignorant of its origin story, including which stellar system it originated from, how long it has been traversing the galaxy, or the environment in which it originally formed. Each of these unanswered questions hinders our ability to differentiate between various hypotheses. A small, highly reflective body would perfectly align with the artificial sail hypothesis, but would be highly improbable as a naturally occurring comet. Conversely, a large, porous object rich in volatiles would be more consistent with natural outgassing, yet it struggles to explain the absence of a visible coma. A dense, rocky entity containing embedded volatiles might account for unseen venting, but then raises questions about its ability to retain ice. An object with an unusual composition, perhaps abundant in carbon monoxide or nitrogen, could generate high-velocity gas jets that escape detection, but it should still exhibit spectral signatures. Until we can establish these properties, our models are built on shaky ground. Therefore, what should we be observing in the upcoming 12 months? Primarily, we need updates on its orbital path. NASA's Jet Propulsion Laboratory's Horizon system continuously refines trajectory calculations as new astronomical observations become available. If the trajectory of Oumuamua, using a placeholder for 3I Atlas as it's a known interstellar object example that fits the context, shifts, if its non-gravitational parameters change, or if the parameter A3, which represents the non-gravitational acceleration, alters from 0 to a non-zero value, these modifications would be highly diagnostic. A transition from planar to three-dimensional thrust would suggest a change in outgassing geometry, perhaps as different sections of the nucleus are exposed to sunlight. Sustained planar thrust would bolster the argument for either precise geometric alignment or active control. Trajectory alterations resembling deliberate maneuvers, with sudden velocity adjustments aligned with specific objectives, would constitute extraordinary evidence supporting the propulsion hypothesis. Secondly, dedicated telescope campaigns are essential. Several major observatories have allocated observation time or could propose observations of Oumuamua. The James Webb Space Telescope, with its remarkable infrared sensitivity, could detect thermal emission from the nucleus, thereby constraining its size and temperature. It could also search for faint molecular emissions in the infrared that ground-based telescopes might miss. These could include gases like carbon monoxide, methane, or carbon dioxide, which sublimate readily but emit weakly at visible wavelengths. Large ground-based telescopes equipped with adaptive optics, such as the Keck telescopes in Hawaii or the Very Large Telescope in Chile, could attempt resolved imaging to discern the nucleus as more than just a point of light, searching for any coma structure, jets, or elongation that might indicate its shape or activity. Spectroscopy across ultraviolet, visible, and infrared wavelengths would help construct a comprehensive picture of Oumuamua's composition and whether it is exhibiting venting. Thirdly, photometric monitoring is critical. Continuous measurements of its brightness over several months can reveal its rotation period through variations in its light curve. This can also constrain its albedo by comparing its brightness at different phase angles and detect any shifts in its activity level. If Oumuamua suddenly brightens, it could signify a new outburst, delayed venting triggered by subsurface warming or fragmentation. If it fades more rapidly than anticipated, it might suggest a change in its reflectivity or orientation, which would be relevant for assessing the sail hypothesis. Fourth, radar observations could provide invaluable data. Planetary radar systems, such as the Goldstone Solar System, radar in California, or the Arecibo telescope before its unfortunate collapse, have been used to observe asteroids and comets, yielding direct measurements of their size, shape, spin, and surface roughness. Goldstone remains operational and could potentially detect Oumuamua if it approaches sufficiently close and is large enough to produce a detectable signal. Radar would definitively constrain its size and reveal whether the object is elongated, spherical, or irregularly shaped, information vital for distinguishing between hypotheses. Fifth, AI-driven surveys and archival searches are crucial. As discussed in Part 11, machine learning algorithms are meticulously sifting through archival data from sky surveys, specifically looking for anomalies. It is plausible that Oumuamua was imaged months or even years ago during its inbound journey, but these observations were not recognized or flagged at the time. Recovering pre-discovery images would extend the observational timeline, improving orbital solutions and potentially indicating whether the non-gravitational acceleration began gradually or abruptly. AI might also identify similar objects in ongoing surveys, and the discovery of a population of such objects would fundamentally alter our understanding. If Oumuamua is one of many, we would be observing a class phenomenon rather than a unique event. Sixth, solar and heliospheric monitoring is important. Tracking solar activity, including flares, coronal mass ejections, solar wind conditions, and their timing relative to any changes in Oumuamua's behavior, could reveal correlations. If the object's acceleration increases or decreases in response to solar events, it would suggest environmental coupling. If it remains independent of solar variations, that would argue for intrinsic mechanisms, either venting or propulsion driven by internal processes. Seventh, theoretical developments are undoubtedly underway, with papers being written to model different scenarios and test whether specific compositions or structures could reproduce the observed phenomena. Publications in prestigious journals like Nature, Science, the Astrophysical Journal, or Icarus will present competing interpretations, leading to community debate. While consensus may or may not emerge, the theoretical work will sharpen our understanding of what is physically possible and what is implausible. Eighth, mission proposals could be considered. Although unlikely, it is not impossible that space agencies might expedite a mission to intercept or observe Oumuamua more closely. Interstellar objects travel at high speeds and are difficult to reach. However, if Oumuamua is deemed sufficiently significant, a flyby mission utilizing existing spacecraft or a rapid response probe could be proposed. The European Space Agency's Comet Interceptor mission is designed for such opportunities, though its launch is not scheduled until the late 2020s. Nevertheless, the prospect of close-up observation, even from a small CubeSat, could provide definitive answers. Now, let's consider potential scenarios for how this might unfold over the next year. Scenario A, natural explanation confirmed. High-resolution imaging or spectroscopy detects a faint coma or jets that were previously below the detection threshold. These jets are found to be oriented in such a way, due to the nucleus's spin and shape, that they produce a net thrust confined to the orbital plane. The composition is revealed to be rich in supervolatiles like carbon monoxide, explaining the high-velocity venting and low dust production. A detailed model incorporating all these factors successfully reproduces the observed acceleration, and the mystery is solved. Oumuamua becomes a spectacular example of an unusual but ultimately natural interstellar comet, teaching us that our assumptions about cometary behavior were too narrow. The object enriches our understanding but does not revolutionize it. Scenario B, exotic explanation gains credence. Photometric observations across multiple wavelengths reveal an unusually high albedo, approaching 90 or 100%, far exceeding that of any natural comet. Phase curve analysis indicates that Oumuamua reflects light like a smooth, flat surface, not a rough, irregular rock. Thermal measurements suggest very low mass, implying an extremely low density inconsistent with solid ice or rock. Collectively, these findings point to a thin, lightweight structure, such as a sail. The scientific community will debate whether such a structure could form naturally, perhaps as a frozen sheet of volatiles in interstellar space, or whether it is artificial. No immediate consensus will emerge, but the sail hypothesis will become the leading explanation, initiating a new chapter in the study of interstellar objects and raising profound questions about whether we are observing technology, either ours or someone else's, adrift between the stars. Scenario C, no decisive resolution. Additional observations will refine constraints, but will not definitively favor any particular hypothesis. The coma will remain absent or barely detectable. Albedo measurements will be inconclusive. Non-gravitational parameters will continue to be puzzling. Oumuamua will fade as it exits the inner solar system, becoming too faint for detailed study. The object will remain a mystery, classified as an anomaly that could not be explained with the available data. Years later, when superior instruments or more examples become available, scientists will revisit Oumuamua. However, in the immediate term, it will be an unsolved puzzle, a frustrating reminder of the limitations of our current observational capabilities. Each scenario carries distinct implications. Scenario A, the natural resolution, would be the most scientifically satisfying in certain respects, demonstrating that nature is stranger and more diverse than we had realized, yet that our physical models are fundamentally sound. It would encourage observers to scrutinize future interstellar objects more carefully, to refrain from assuming comets will vent visibly, and to anticipate the unexpected. Scenario B, the exotic resolution, would be transformative. If Oumuamua is a sail, whether natural or artificial, it compels us to broaden our thinking about what exists in the galaxy, how matter structures itself on large scales, and possibly whether intelligence is rare or common. The implications would ripple outwards into philosophy, astrobiology, and technology. Scenario C, the unresolved mystery, is the least satisfying but perhaps the most realistic. Scientific progress is often slow, constrained by resources, technology, and the sheer difficulty of observing distant, faint objects. Not every question is answered immediately, and some remain open for decades. Beyond the immediate resolution, Oumuamua raises broader questions about how we search for and interpret anomalies. This object was detected because our monitoring systems are sufficiently advanced to identify minor deviations from gravitational orbits, and because the astronomical community is attentive to interstellar visitors. But how many anomalies do we miss? How many objects pass unnoticed because they are faint, their behavior is subtle, or we are not observing at the appropriate wavelengths? The answer is undoubtedly many. The sky is vast. Our surveys cover only fractions of it at any given time, and small bodies are difficult to track. Enhancing our detection capabilities, constructing larger telescopes, deploying more sensitive instruments, and employing AI to analyze data all expand our reach. Each improvement increases the probability that we will discover more objects like Oumuamua, or even stranger ones. And with each discovery, our classification of what constitutes normal expands. What once seemed impossible becomes possible. What once seemed unique becomes part of a pattern. This is the trajectory of science, moving from ignorance to partial knowledge to deeper understanding, always provisionally, and always ready to adapt when new evidence emerges. There is also a meta-level question regarding how science addresses the extraordinary. When confronted with an anomaly that challenges established assumptions, how do we balance skepticism with openness? Excessive skepticism may lead us to dismiss genuine discoveries prematurely. Excessive openness can result in wasted time pursuing false leads and pseudoscience. The peer review process, public debate, and replication of results serve as safeguards, though they are not infallible. Careers, funding, and reputations are at stake, creating social pressures that can compromise objectivity. Oumuamua tests these dynamics. Natural hypotheses represent the safe choice, explanations that align with existing frameworks and are predisposed to community acceptance. Exotic hypotheses are riskier, demanding more evidence and facing higher publication barriers. Frontier physics hypotheses are the riskiest of all, invoking novel mechanisms that most scientists deem improbable. Nevertheless, all three categories warrant consideration, evaluated on their merits against the available data. The challenge lies in maintaining that balance, avoiding both premature dismissal of ideas and uncritical acceptance. For those of us observing from outside the scientific community, Oumuamua serves as a reminder that the universe is replete with surprises, that our knowledge is incomplete, and that the boundaries of the known are where the most interesting discoveries are made. It also reminds us that science is a human endeavor shaped by the individuals who practice it, with all the creativity, bias, passion, and limitations that entails. We should celebrate the progress science makes while acknowledging its imperfections. So, as we conclude this exploration, here is a question to ponder. Are we observing not merely a comet, but a signal of something new entering our solar neighborhood? Something that defies our classifications? Something that compels us to think more broadly and more unconventionally? Perhaps Oumuamua is simply a comet, an unusual one, but ultimately natural. Perhaps it is something else entirely. A sail, a probe, a fragment of extraterrestrial engineering, or a manifestation of physics we have yet to comprehend. The data does not yet provide a definitive answer, but the fact that we are posing these questions seriously and rigorously is significant in itself. The next 12 months will bring new observations, new analyses, and new debates. Stay tuned. Follow the updates from JPL Horizons. Look for scientific papers from researchers studying Oumuamua. Listen to the discussions within the astronomical community. The story is still being written, and you are witnessing its unfolding in real time. Science at its finest is a collective human endeavor to comprehend reality, and mysteries like Oumuamua are precisely why that effort matters. We stand on the threshold, gazing at a visitor from the stars, attempting to decipher its secrets. It silently accelerates through the darkness, confounding our expectations, whispering that the cosmos holds more than we ever imagined. Whether it is a cosmic anomaly or a cosmic message, time and further observation will tell. But for now, we watch, we wonder, and we wait, knowing that the universe has surprised us before and will undoubtedly surprise us again. and that each surprise brings us one step closer to understanding our place within the infinite expanse. The anomaly of Oumuamua is not merely a scientific puzzle, it is an invitation to look more intently, think more deeply, and remain humble before the immensity of what we do not yet know. And that, ultimately, may be the most important lesson.